Okay, so here we are at the spinny marble. Um, do a diagram of the marble. Is do all of the sort of accelerations. So here's mass times acceleration tangential. Here's mass times gravity. Here is mass times acceleration radial. So you can see here we have an angle like this. It's telling us that the radial acceleration is a component of the gravity. So you can draw this triangle in a couple of different ways. But what you have here is, if you want to make this the hypotenuse over here, you have mg cosine theta. It's going to be the mass times acceleration in the radial. You could also choose to make the acceleration in the radial the hypotenuse, and then you would have a little bit of a different way of getting this over in this direction. But really you can do it either way. If I say that this is the hypotenuse, then I would say r sine theta is mg, where r is the larger value. If I do with the cosine, then the radial acceleration is the smaller value. So if this, we want this initial value here in the main direction to be the larger value. So what we have, we can sum forces in the radial equal to mass times acceleration in the radial. And what we have also is a component here that we're not considering, which is going to be v squared over r, mv squared over r, which is the component of acceleration that is caused by this object accelerating outward here, where you can see this outward acceleration has a component, is if we draw the components is this way here, and then this way here, there's a component of it that goes outward, the opposite of gravity, where gravity is going down and inward. So that's what this is, and that's mv squared over r. So what we have is we have a we're going to say positive is outward and negative is inward. This, so what we have is we have a positive mv squared over r. We have a negative mg cosine theta, and then we have a plus or minus friction. And all of this is equal to mass times acceleration in the radial. So what we can do is we can divide out mass. And what we have is acceleration in the radial is equal to a positive v squared over r, negative g cosine theta, and then plus or minus uk normal. So if the gravity component is greater than if this gravity component here is greater than this, then the motion is inward, so the friction is positive. So if the ball is falling towards the middle, then the friction must be positive. Okay, so at this stage, the next step is to use our coordinate equations. We have a distance radial, we have a distance tangential. And I don't want to do anything with an angle because that's going to make it more complicated. I just want to do a straight distance around like this, which is the tangential distance, and then a distance down inward, which is the radial distance. So our basic equations are at squared over 2 plus v0t plus the initial position, which is going to be the radius, the initial radius. And then over here we have at squared over 2 plus v0t plus the initial position tangentially, which we can say like here's 1, and then we're going all the way around to 2 pi or something like that, like distance around. Or radians is like just a straight distance. But I'm not going to do it, the answer in terms of pi. I'm just going to get a straight answer. So at this point, what I can do is I can know that the initial distance is the maximum value of r. The minimum distance is when the ball's in the middle, where r is equal to 0. So that's equal to 0. What we have now is ax squared plus bx plus c, which is the quadratic formula with t. So you have a negative b plus or minus the square root of b squared minus 4ac all over 2a. You can solve that for t. Okay, so we have t now that is known, quadratic formula, and we can plug that value for t back in over here, and we can find the final position as distance traveled of the ball rolling around. And that's what we're trying to solve for, is the final position of the ball that's rolling around. And then you can alter the equation where it's like a science experiment where I'm dropping the ball at t equals 1, and then I'm stopping the timer at t equals 2, and I'm saying what is the delta r, r2, r1, and then delta r is I can know that because I can measure where it is at the start, and then I can mark it at the stop, and I also have time. What the unknown is the angle of the cone, so I can plug in the knowns, which is the time and the distance, and then solve backwards to find this angle from this cosine here. So what I'm missing here is acceleration tangential is just the initial acceleration minus mu kg, where I'm canceling out the m from both sides. So that's what I would plug in here for this tangential acceleration. Is the only thing slowing the tangential motion